In this video, we're going to do another example of finding where a function is increasing and decreasing by using the first derivative test. So first of all, to do the first derivative test, you need to find the critical points. So how do we find the critical points? That is found by looking for where the derivative, first derivative, is 0 or undefined. Okay, so let's find the derivative. So f prime is equal to the derivative of sine, cosine, minus the derivative of cosine. That's negative sine. So two negatives is going to make this a positive sine of x, and there's your derivative. Now, this derivative could be 0. We're going to solve that equation. So let's set it equal to 0. But what about undefined? Is this derivative ever going to be undefined? Cosine is defined everywhere. Sine is defined everywhere. If you add them together, you'll always get a value. So undefined in this case is not something we need to consider. This will always be defined. All right, how do we solve for solve for x? Well, problem is x is inside of sine and cosine. You've probably seen this before in your homework. If you have two trig functions and your variables inside both of them, you need to somehow use a trig identity in order to get the two trig functions combined into one. So what can we do? Well, there's no way to put these together with just adding cosine and sine. You could do something crazy like multiplying by the conjugate, but I think there's something simpler we could do. Let's try taking one of the trig functions around to the other side of the equal sign. So let's bring sine around, and it becomes negative. Now I see that I could actually divide both sides by one of the trig functions. If I divide by cosine, for example, I end up with sine over cosine. That's something that we should know. So we now have 1 equals negative. What's sine over cosine? Tangent. If you don't remember that, you need to review your trig identities. Negative 1, if we bring our negative sign around, is equal to tangent of x. Now you could do the inverse tangent, but basically you're just trying to figure out what x values make tangent equal negative 1. So if we go around our unit circle, tangent is negative in the second quadrant because sine is positive, and cosine is negative. And then the fourth quadrant because cosine is positive, but sine is negative. So we are in these two quadrants, the second and fourth. Tangent is negative 1 when sine and cosine have the same value. So that means we are actually exactly halfway through this interval. Because at this point, sine and cosine both have the same value. We're also halfway through this quadrant. Again, sine and cosine would have the same value at that point. What points are these? Exactly halfway through, the referencing will be pi over 4. So we're pi over 2 and another pi over 4. So this is actually 3 pi over 4. And this one is just pi over 4 short of the 2 pi mark. So this is 7 pi over 4. If you need to mark the other ones in between, pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4, you can do it that way too. How you do it is up to you. Alright, so what this means is we found 2 points, x, in this interval from 0 to 2 pi. If you go around the circle again or you go negative angles, there'd be more options. But in our interval, we found that x equals 3 pi over 4 and 7 pi over 4 are the critical points for this function. Critical points. Once you have your critical points, you can then identify the open intervals where f is increasing and decreasing. The way I like to do this is by building the sine chart for the first derivative. So sine chart means you draw your number line, put your critical points in order on the number line. So our critical points were 3 pi over 4 and 7 pi over 4. I like to draw vertical lines to help denote that these are the points where we can change from increasing to decreasing. At these points, the derivative is 0. So what we have to do to fill in our sine chart is we have to evaluate some test points. So pick a point to the left, in the middle, and to the right. Remember, we're between 0 and 2 pi, so don't go too far. 0 and 2 pi are the bounds. But you could do 0, and you could do 2 pi, absolutely. And then in between 3 pi and 7 pi over 4, let's see, 3 pi over 4 is here, 7 pi over, we could do pi. That's not too bad. Nice numbers. Remember, when you're building your first derivative sine chart, you evaluate the first derivative. So our first derivative we already found was cosine plus sine, and we're going to plug in our values. So f prime at 0. So cosine of 0 plus sine of 0. Cosine at 0 is 1, sine at 0 is 0, and we get positive. That's all we need is the sign. So positive here. Evaluate at your next test point, pi. So cosine of pi plus sine of pi. Let's see, at pi, cosine is -1, sine is still 0, so we get a negative in the middle here. One more test point, 2 pi. All right, so we need cosine at 2 pi plus sine at 2 pi. That's 1 and 0, which make a positive answer. So we have positive. Now, you might be seeing some patterns in your sine charts. Very often, the signs will alternate in your sine charts. However, there are cases where the signs will not alternate, so you must be cautious about assuming that they're going to alternate. Squares in your problem can make a huge impact on whether or not these are going to alternate. So just be cautious. Always test until you have learned what to watch out for. Okay, so what do these mean? When the first derivative is positive, what does that mean about the function? That means we have a positive slope. The function is increasing. Negative derivative means you are decreasing. Positive slope, you are increasing. There you go. So we've identified the intervals. We can write them down. So let's do that. So we are looking at increasing interval. Now start where your domain starts, 0. They want open intervals, so remember open means parenthesis. So from 0 to our first critical point, 3 pi over 4, we are increasing. Then we are decreasing from 3 pi over 4 to 7 pi over 4. And then we are increasing again from 7 pi over 4 to the end of our domain, which was 2 pi. Again, parenthesis only because they specified they wanted open intervals. So that's it. Part C asks us to find the local extreme values. So do you remember how to determine if the critical point is a local extreme value? It's determined by the fact that your signs change. So we change from a positive derivative to a negative. So you're increasing, then you turn around, you come back down, you're decreasing. What does that mean 3 pi over 4 has to be? You go up to the point and then you go down. So this is actually a maximum point, at least a local max. We're then decreasing to our next critical point and then go back up from there, which means that that would be a min, or at least a local min. So the actual extreme values, though, are not these values. The actual extreme values are the function values. This is where it happens. So we have a local max at x equals 3 pi over 4, and a local min at x equals 7 pi over 4. But you want the actual values that are achieved here. The actual values are always the y value. So the max value, or max local value, is y equals your function, the original function evaluated at x. So remember, the first derivative sine chart, you evaluate the first derivative. To find the value of the max and min, you have to go back to the original function. So let me write these two down, and then we will go find our original function. So we're also going to plug in our local min location of 7 pi over 4 to find the actual local minimum value. All right, what was our function? Sine minus cosine. So we have sine of 3 pi over 4 minus cosine 3 pi over 4. So what is sine at 3 pi over 4? Well, that's second quadrant. So sine is positive, and pi over 4 is the reference angle, so square root of 2 over 2. Minus cosine there is actually negative. So we have another negative, and pi over 4 is the reference angle, so square root of 2 over 2. So if you don't remember how to evaluate a trig function for the exact value, you probably need to go review that. Find a video. I have some videos about that. If you need me to help you find it, let me know. So these two negatives make a positive. So we have square root of 2 over 2 plus square root of 2 over 2. Or add the coefficients together. 1 plus 1 makes 2 square roots of 2 over 2. Or square root of 2. That is our local max. We do the same thing for our local min. We evaluate our function at 7 pi over 4. So sine, let's see, 7 pi over 4 is in the fourth quadrant. Sine in the fourth quadrant is negative. So negative square root of 2 over 2 minus cosine in the fourth is positive, so square root of 2 over 2. They have the same sign, so we add them together just like before. So negative 2 square roots of 2 over 2. 2's cancel, and we get negative square root of 2. And there you go. That's another example of how to use the first order test to determine where your function is increasing and decreasing. We're going to do more of these as we work our way through this topic of eventually graphing the curves. So you will see more examples, but make sure you practice. And if you ever feel like you know how to do a problem, you can always pause the video and try it on your own, then come back and see if you got it right. All right, that's it for this video. I'll see you in the next one.